record. All right, I'm not on mute. Things are looking up. Friday the 13th today. How's it been? Didn't notice. Can't say I noticed. Way back when I had laser eye surgery, I had it on a Friday the 13th because they had lots of openings. Like, yeah, I'll do that. No problem. Okay. So usually I do a little bit of review, but we're going to kind of check in on what we did last day later. And so we'll kind of keep using it. But what did we talk about? I guess I will do review. What did we talk about? Talked about, no, seriously, what did we talk about? I can't remember. We talked about numeration systems. I think we talked about converting from base 10 to other bases. And from base 2, but other bases, I think, as well. Man, I really should have reviewed myself. Yeah, you remember. We talked about binary numbers, right? This is in base 4, right? But then we went from base 4 to base 10. Looks like binary, but it's not. It's a decoy. And then from base 10 to base 2 or any other base by long division, right? Or using your calculator. It's one of those buttons that you have. Might be worthwhile getting to know your calculator. So today I want to talk about binary arithmetic, or that's where we'll start. And so what's nice is we really only need addition and multiplication. And addition is almost the weird one. So addition, let's make a little table here in binary, right? If I want to add two binary numbers to look at all the possible combinations that I can have, right? I just need to make a little matrix, 0, 1, 0, 1, right? And then I can think about, okay, what does 0 plus 0 look like? This behaves the exact same way that we would expect it to. 0 plus 0 is, in fact, 0. Right? Base 2. How about 0 plus 1? 1. Base 2. How about 1 plus 0? Probably 1. Order doesn't matter, right? The only pickle, 1, 0. I'll do it in green so we can kind of, since 1 plus 1 is 2, but 2 is 1, 0 in base 2. So that's the only sneaky one, I think. We'll make a similar matrix for multiplication. 0, 1, 0, 1. But multiplication is nice because there's really no curveballs here, right? 0 times 0 is still 0. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. Not a ton of options there. So we can use these to do some examples, right? So here Nothing crazy is going on here. Let me just, this looked like it slipped down a little bit. Still not that nice. It's just that 1 plus 1 is 1, 0 base 2. All right. So if we have to do 1, 1 base 2 plus 101 base 2, I'm going to set it up like this. 1, 1 base 2 is kind of understood at this point. You can write the base 2, but as long as you're keeping track. One plus 1, we just said, is 1, 0. But what we need to do is we need to carry that 1 over. So here, I'll explain that since 1 plus 1 is 2, which is 1, 0 base 2. Again, we write 0 and carry the 1. After that, I have 1 plus 1 plus 0. That's fine. Now we know what to do here. 1 plus 1, again, is 1, 0. Not being lazy. Could have written this up here, carried it down. Huh? Nice. How about some multiplication? I'm going to set it up the same way. 1, 1, 1, 0, 1. And could have used a little bit more space, I think. So I'm going to just bump it up here. Why do I need space? I need to do a couple of times over. So, been a long time since we've multiplied by hand, probably. Gotta go through, tedious, not hard, but tedious, right? And so what are we gonna do? 1 times 1, 1 times 1, 0 times 1, 0 times 1, 1 times 1, 1 times 1, and then we have to collapse those. Let's see if I can use a different color here. So 1 times 1 is 1. 1 times 1 is 1. 0 times 1 is 0. 0 times 1 is 0. 1 times 1. 1 times 1 is 1. To make sure my stacking is good. And then 1 times 1 is 1 again. And then I add those, right? 1, 1, 1, 1, base 2. Can do the next one too. I'll give you a minute to try it. It's gonna be a little bit longer. Try not to go cross-eyed. Did you get 1, 1, 0, 1, 1, 1, 0, base 2? That's a relief. I think if I had done it wrong, I would have had to just start over. There's no way to untangle that mess. I'll bump this up here. Okay. Any questions about binary arithmetic? Okay. So in general, when we convert between two non-10 bases, we're still going to use base 10 as kind of a gateway. You don't have to if you have a quicker method, but as always, this will always work. You can always do this. Tedious, and so I've got a couple of shortcuts for some go-tos like octal and hexadecimal. Okay, but just to show you how it would work, right? What would you need to do if you want to convert 3464 base 7 to base 5? What would you need to do? You could convert this base 7 to base 10 and then to base 5, right? Base 10 by using those exponents, and then going back to base 5 by dividing by 5 and looking at the remainders, right? So let's see it in action. You can try it. How about this? You try it. I'll write out my version and then we can check in again. Then you can have some time to try it. But it's going to take me some time to write it out. That's why. Let's see here. Oh. Too many arrows. Okay, let me bump this. I needed more room. So step one, a little refresher. How do you convert to base 10? Well, this is in base 7, so you're going to use the powers of 7, not forgetting about 7 to the power of 0, right? And then 7 to the 1, 7 to the 2, 7 to the 3, and then write it out in expanded form. This, and then you can just add these up, and that'll be in base 10. Now you have something that you're familiar with, right? Used to working with. Now we wanted it in base 5. Nope. Yes, base 5. So then we're going to take this 1271 base 10 and convert it to base 5 by repeated division. I had to do it down here. So I have seen, what did it look like? I think it looked like, I have seen this, which might be nice, but then you have to read it from the bottom up. That doesn't matter, but maybe it's nice for kind of figuring out your spacing, right? Then it would look like 254, right? And so on and so forth. And so that's just another way of writing it. This way. I can see that because it makes the spacing a little bit easier. Otherwise, I have to kind of judge how many times. Well, I'm on an iPad, so I can just resize things and make it work, but that's not cool. However you want to do it, totally fine. Right. It's cleaner. I'll give them that. This is how I learned it, so stuck. So repeated division, keeping track of your remainders, right? And then the remainders will be the values that we're interested in, and then we read them from, in this case, because I divided from the bottom, right? I have to read them going down, right? And so then I get 20041 base 5. Yes. Okay. Maybe you know the shortcuts already. Going between binary and octal, for example. Do you know the shortcuts? Not yet. Haha. Okay. I'll beat them to the punch. And I love that. Can I remember what was supposed to go here? I don't think there's anything. Sorry. Wasted paper. I'm going to make a note here. Wasted space. Could use it for something. Draw a doodle or something. A doodle? Yes, an original doodle. Okay. Yeah, I don't have anything to put there, so no original thoughts here. So what you're gonna do, so the shortcut from binary to octal, pretty limited uses, of course, but moving between these, what are you gonna do? You're gonna divide your binary digits into groups of 3. I'll highlight the 3 because spoiler alert, when we go to hexadecimal, we do the same thing, but groups of 4, right? If you think about binary 1, 1, 1, 1, 1, 16, right? 1, 1, 1, groups of 3, 8, okay? And so starting from the decimal point, and then you're gonna add leading or trailing zeros if you need to, okay? And what you're going to do is you're going to convert each group of 3 binary digits into 1 octal digit. Right? And so let's see here. I know what I can use this space for. Notice 1, 1, 1 base 2 is 2 to the 2 plus 2 to the 1 plus 2 to the 0, which is 4 plus 2, which is 6 plus 1. Did I do that wrong? Yes, I did. 2 to the 0. I did it completely wrong. Don't do what I did. 1 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. Why isn't it? I'm trying to get to 8. It's fine, guys. It's supposed to go to 7. Okay. Been kind of a long week, I guess. There, I was trying to show something, and then like, no, this is how it works. Because 0 to 7 makes 8. Should have just left it alone. Okay, so using this shortcut, right? What could you do if you don't remember the shortcuts? Perfectly reasonable to move from base 2 to base 10 to base 8. That's fine, right? This is just a shortcut. So you already know how to do this one way. Here's another way. All right, so I'm gonna write these out a little bit bigger. 1, 1, 0, 1, 1, 1, 0, base 2. And then what we're gonna do is we're gonna make groups of 3 starting at the decimal point or where it would be, right? And so of course that would be here. And I'm gonna make groups of 3. Adding, trailing, or leading zeros if you need to, right? Which we do in this case. Maybe I'll do those in orange. So groups of 3 digits. Just so I don't muck it up again, I'm gonna do the powers of 2 underneath. A little bit overkill, I think, even at this point, but I need it. And I get to do whatever I want. It's my work. I'm not going to write out the expanded form, right? That's probably enough for me to look at, right? But now I'm going to do 0 times 4 plus 0 times 2 plus 1 times 1 makes 1. 1 times 4 plus 0 times 2 plus 1 times 1 makes 5. One times 4 plus 1 times 2 plus 0 times 1 makes 6. I think you might even already be at the point where you're looking at these binary numbers and you can just see what they are, right? Especially in these lower digits, but that's okay. So by this shortcut, the answer is 156 base 8. So even though we convert it to base 10, but then kind of hangs out in base 8 anyways. Can confirm it using your calculator. I'm not going to do that because I've got my kind of rickety setup here, but you can confirm it, be convinced. How about this? I'll leave that one for you to work on either at the end of class or later. I'll post the notes. If you had to guess, well, I guess you don't have to guess because it's in the notes, but how would you undo what we just did? You just go the other way, right? And so to go from octal to binary, you're going to convert each octal into a 3-digit binary and then just smush them together. Okay. And so let's see, maybe something like 7, 1 base 8, 7. I did just establish that that's going to be 1, 1, 1 base 2. So binary. And 1 is 0, 0, 1 base 2. Okay. So now this becomes 1, 1, 1. I'll do a little space, mostly for visual cues. It doesn't mean anything, but just to keep these groups of 3 separate a little bit. 0, 0, 1 base 2 for binary. Yeah. Always 3. Always groups of 3 for octal, and then groups of 4 for hexadecimal. So if you have 1101.01, let's say, then you would have to add trailing zeros. So you start in both directions, or let's do octal, just 3. You start at the decimal, and then you add leading and trailing zeros as necessary. Nice. You know what I'm going to do? I'm going to Well, it's not very beautiful, is it? But I'm going to move this up here with so for example, with that little blurb, just to show what that means. Nice. I'm trying to let you guys fly on your own, but I'm pretty micromanagey. So I'm gonna try to be cool and star these and then give you time to work on them later. Or try them now. We're gonna do the same thing. So for between binary and hexadecimal or hex is base 16. And I know hex is for colors, right? Thank you. You can sense my, I think it's for colors, mainly. I'm sure there are other things you could use it for, but not my domain. So, but we do need 16 symbols. Okay. And so I cheated and I pulled this in already, or wrote it out already. So in base 10, we go up from 0 to 15. And of course the hex gaps out after 0 to 9, but then we switch to A, B, C, D, E, F, okay? Taking the place of 10, 11, 12, 13, 14, 15, base 10. Okay? I have written out the binary for it as well, and just as we're getting started, but of course you should be able to kind of go between, well, base 10, but also hex to binary probably pretty quickly, I assume. I don't know. Besides teaching you this, we're not really going to use it that much. So see it on a test. I had an idea, but I haven't fully formed it. So I introduced it in class, of course, where as part of an assignment, you have to make questions with solutions. And then we would just put them all in a pot on Moodle. And then for the tests, I would pull from those. So we create our own question bank. I think that's kind of fun, right? So think about what your question would be and what the solution would be. The reason I want to do that is because it's so useful to think about, okay, well, what would a test question look like, right? And so that seems silly, but sometimes it feels like, oh, well, how should I know, right? But if we've kind of generated this question bank together, or not together, on your own, I'll check them, and then I'll pick from that pot. That's what I'm thinking. That's something I'm playing around with. We'll see. It's just an idea I had. You already know, because I gave you a spoiler. To go from binary to hexadecimal, you do the same thing, but you want to go into groups of 4 digits, right? And again, adding trailing or leading zeros as needed. And then you're going to convert each group of 4 digits into 1 hexadecimal digit. Let's do this one together. And you can use the, how about this? I'll keep that on the page, and then I'll copy this so that we can have it both on. Although I guess you have this in front of you. but might be helpful just so you don't have to convert to binary. Good practice. Mhm. You're allowed to use your calculator. What would a good question be? A good question might be this one. I'd say this is a kind of a hard question, right? Because there's kind of no shortcuts, there's no calculator buttons for it, right? Where you have to convert from a non-button base to another non-button base, right? This way I can test you, well, do you know how to convert to base 10? And then do you know to go back to the new base, right? So I would consider this a good, solid question, or like that type of question. Yeah, you always have to show your work. I do like to throw some kind of quick ones in there as well, where you could just use your calculator. Then I'm just looking for the answer, right? But for something like this, kind of lengthy, covering two concepts, right? That's a moneymaker of a question right there, right? And so, yeah, there will be quick ones, and I'm just looking for the answer, but sometimes you'll have to show work if you need to do work. Good. Where was I? Oh, yeah. Maybe you're just so fast and you wrote these all down already. Or maybe you can just do it. Who knows? But let's see here. Oops. I'm gonna write these out a little bit loftier here. 1, 1, 0, 1, 1, 0, 1. Groups of 4, here we go. I'm not very quick on the conversions. But I get 6D in hex. You should be able to check that on your calculator, right? Or if your calculator doesn't do it, that's totally fine. You've got this shortcut. Hex to binary, you guessed it. Just undo what we just did, right? And so convert each hexadecimal to a 4-digit binary and then just smush them all together. And then there you are. C45 hex. C is 12 base 10. But if I didn't have that table, right, then what would I need to do here? I would need to say, okay, to convert 12 to base 2, I can do long or repeated division. 2 goes into 12 6 times with a remainder of 0. 2 goes into 6 3 times with the remainder of 0. 2 goes into 3 1 time with the remainder of 1. So I get 1 1 0 0. You can confirm with that table if you want. 4 is at this point kind of relatively easy. 0 1 0 0. Same with 5 0 1 0 1. Putting me at 1 1 0 0 0 1 0 0 0 1 0 1 base 2. And then there's just a bunch more problems. Womp womp. Do you want to work through them together or on your own? I got a finger wag. I am going to stop the recording, I guess, because this is pretty boring. But I'll give you time to work through those, and I'll just kind of write them out, but without reading them out, so I'm not disturbing you. But I will stop that here.